going to be a valuable resource.
So yeah, I don't see the chat. So if there will be some questions in the chat, let me know.
I think everybody can talk. Usually there are not many interruptions during the talk, but okay, yeah, chat or just speak out. Anything.
Yeah, okay. Yeah, ready.
Maybe we can start. So welcome everyone, and today we have Marianna Russkikh from MIT. She's gonna give us a crash course on timers and how to embed them.
Yeah, thank you very much. My talk is based on joint project with Russkikh, Kenyon, Wayne Lam, Benoit Lallier, and Sanjay Ramasamy. And let me start with some basic definitions, even though you know them, just to fix the notation and to be sure that we're all on the same page. Okay, a dimer configuration is a subset of edges that covers every vertex exactly once. And a dimer model is a random covering of a given graph by dimers. And today we're going to deal only with planar bipartite graphs. And two prototypical examples are the dimer model on the square lattice and on the hexagonal lattice, also known as domino tilings and lozenge tilings. And indeed, it's easy to see from this picture that instead of a dimer configuration on a subset of square lattice, one can think about domino tilings of a discrete domain on the dual lattice. And similarly, lozenge tilings of a discrete domain on the dual lattice, which is a triangle lattice in the case of the honeycomb. One can use this interpretation in general as well. So we can always think about domino tilings of a discrete domain on the dual lattice instead of dimer configurations. And here, each domino is a union of white and black face. And this is how I'm going to think most of the time about the dimer configurations. Instead, I want to think about domino tilings. Okay. The main object of our interest is the height function. Let me show you one of the ways to define the height function. So the height function is the integer valued function defined on the dual graph of the bipartite graph where dimers lives. And to define it, let us fix a reference dimer configuration, a blue one on this picture, and consider a superposition of a fixed one with a random one. So then clearly we obtain a set of loops and double edges. And those loops can be easily oriented. Just orient all edges of fixed configuration from white vertex to black one, and of a random one from black one to a white. So we obtain orientation of loops. And now the height function change by plus or minus 1 if we cross a loop, depending on the orientation of the corresponding loop. So here is an example. And this definition allows us to give a random surface interpretation for a height function just using the height as a third coordinate. Note that the fluctuations of the height function do not depend on the choice of the reference configuration. However, the height function itself, of course, depends on the choice of the reference configurations, but today we're interested in fluctuations only. So the fluctuations of the height function don't depend on the choice of a reference configuration of a fixed one. And the fluctuations of the height function conjecture to converge to the Gaussian free field in some conformal structure. So first of all, what is the Gaussian free field? If you don't know what is this, you can just keep in mind this picture and think that this is two-dimensional. Actually, this picture is the simulation of the discrete Gaussian free field. So, and you can think about it as a two-dimensional version of the Brownian bridge. Okay, more precisely, the two-dimensional Gaussian free field with zero boundary conditions is a conformally invariant random generalized function. Or, okay, there are many equivalent definitions. Let us say that it is a Gaussian process with the green function with the covariance kernel given by a Green's function. And as I said, the fluctuations of the height function conjectured to converge to the Gaussian free field in some conformal structure. Let me explain you the last part of of this sentence. So on this slide, we deal with uniform lozenge tilings of a hexagon. So by uniform, we mean that all configurations are equally weighted. And at a large scale, this is how the picture looks like. So it is known that lozenge tilings satisfy some limit shape phenomena. So you can see some frozen parts near the boundary, and it is homogeneous inside a sublimit shape. In this case, it's a circle, so-called Arctic circle. And the fluctuations of the height function inside this Arctic circle converge to the Gaussian free field, but in the different metric, not in what you get here. So one should map this disk to a unit disk, and here is a precise map. And the only thing which you need to know about this map, that this is not a conformal one. So we really need to change the conformal structure. The fluctuations of the height function converges to GFF in some new coordinates. In general, it is known on periodic lattices that if you think about the height function as a fluctuated random surface, then there is a limit shape phenomenon which I mentioned already. So the random profile concentrates near some surface which minimizing some certain entropy functional. This is what known for periodic lattices. It was proven by Kohn, Kenyon, and Prop, I guess 20 years ago. And there is a prediction that the fluctuations of the height function should converge to the Gaussian free field in some metric, which is non-trivial. This metric can be constructed from this limit shape, from this limit surface in some non-trivial way. However, so this is a general prediction, and it is proven only for certain types of polygons. So what I want to say is that the height function is the Daimer model is very sensitive to the boundary conditions of the microscopic behavior of the boundary. So if you just look at these two pictures, then clearly this shows a different behavior. So in the first one, we can see that the limit surface is a flat one, is a very flat one, I would say. And in the second one, it is not a flat one, non-flat case. And so for a non-flat case, for some boundaries which are polygons, the convergence shown in some boundary for some boundary conditions were some integrable probability and asymptotic analysis. And for the flat case, what is known, there are some results. The first was given 20 years ago. Rick proved the convergence for so-called temporary domains, which gives flat boundary conditions of the height function on the square lattice. However, if you think about most natural types of approximations on the square lattice, let us think about discrete domains which composed of 2x2 blocks. Right, first of all, clearly that such domains have some dominant tilings. They have many dominant tilings, and also in this case, the height function on the boundary is 0. So this is 0 boundary conditions for the height function. And this is an open question. And here people use different approach, which relates to the discrete version of complex analysis and potential theory. And we will see a bit later, then here as well, there is a huge question about boundary conditions, and the combinatorial shape of the boundary is super important. Okay, so all results mentioned here, they are all for periodic lattices, and moreover, all of them here are for the uniform dimer model. What about non-regular generic planar bipartite graphs? Moreover, if we want to deal with weighted dimer configurations instead of uniform one. And here is the goal. We want to draw a graph in such a way that the fluctuations of the height function converges to the Gaussian free field. To get an intuition here, think about random walks on planar graphs. It is known that, let's say, in periodic environment, the random walk on planar graphs converges to the Brownian motion. And the correct embedding here is a TATS embedding. And here is a similar question. So we want to draw a graph in such a way that given a large planar bipartite graph with weights on edges, we want to embed it in such a way that geometric weights given by this embedding define the same probability measure as a given one, and the fluctuations on those embeddings converge to the Gaussian free field. And another question is in which metric? So we claim that t-embeddings, or we call them also circle pattern embeddings, is a good candidate to describe this metric, and a good candidate to be the embedding where the fluctuations of the height function converges to the Gaussian free field. And now there are 3 natural questions. First of all, how to describe those embeddings? What are those embeddings? The second question is whether they exist. And the third question is, okay, to check that indeed on those embeddings, the fluctuations of the height function converges to the Gaussian free field. And here are 2 main results. Indeed, we can show that such embeddings exist at least in 2 following cases. If we start with the finite planar bipartite graph with outer face of degree 4, or for any biperiodic bipartite graph with biperiodic weights. In these 2 cases, we can show that t-embeddings for any given graph with weights exist. And here is the second theorem. Under some technical assumptions and under an assumption that some map which is related to the embedding, I will describe it later, is small in the limit, we can show the convergence of the fluctuations to the Gaussian free field. Now, the goal for the rest is to clarify this slide, to explain all definitions, and to discuss these two main results. Are there any questions so far? Okay. If not, then let me, oops, what's happened? Sorry, something wrong with, I apologize, just a sec. Okay, so what I'm going to do now, I'm going to fix some issues with my PDF. Sorry, guys. I don't understand why in Zoom it doesn't show next pages.
It's only in Zoom, so you can see the
yes. Like when I open it with non-sharing screen, I can see next pages.
What if you just share the screen and so is it because you try to share Adobe?
Yep. Okay, let me try different. Interesting. Never had this problem before. Okay. Do you see it now?
Yes.
Okay. Sorry for that. Let me give you some basic definitions and facts. Just a reminder on on the dimer model, which we need before I go to the new embeddings. So first of all, I said that we want to deal with weighted dimers on planar bipartite graphs. So how we define the probability measure? Given a positive weight function on edges, we define the probability measure as following. So the probability of a given configuration is proportional to the product of its edge weights. Now, note that if we consider all edge weights around a single vertex, and we multiply them by some constant c, then the probability measure doesn't change, right? Because each dimer configuration should cover this vertex exactly once. So we will take only one of those edges. Therefore, each weight of each configuration will be multiplied by the same constant. So we call two functions gauge equivalent if one can be obtained from other by a sequence of such multiplications. In other words, two weight functions are said to be gauge equivalent. Recall that we deal with bipartite graphs. So it is gauge equivalent if there are two functions, one defined on black vertices, another one defined on white vertices. And the weight of the first weight function is the product of functions f, g, and the second one. And yet again, gauge equivalent weights define the same probability measure. Another way to describe a class of these gauge equivalent weights is to look at the phase weights instead. So we can introduce a weight function on phases, which is given by the alternating product of weights along each simple phase. And then note that if two weight functions are gauge equivalent, then this happens if and only if they define the same phase weights on the graph. Okay. Okay. Now one important object on the Dimer model, which is the main object for us to study the height function, is the Kasteleyn matrix. So what is the Kasteleyn matrix? This is a weighted signs adjacency matrix whose rows are indexed by white vertices and columns indexed by black vertices. And each Kasteleyn weight is given by the product of Kasteleyn site and the weight function, where the weight function is our given weight function. So recall that in my definition, this is actually one quarter of the usual adjacency matrix. Because usually, yeah, the first argument is always a white vertex and the second one is always a black one. And Kasteleyn showed that the partition function of the Dimer model can be evaluated at the absolute value of the determinant of a weighted signed adjacency matrix if the signs are chosen to be Kasteleyn signs. So what does it mean that the signs are Kasteleyn signs? First of all, it's easy to show that if we just take a weighted adjacency matrix without any signs, then the partition function is given by a permanent of such adjacency matrix, right? This is just equivalent, the definition of the permanent and the definition of the partition function in this case. However, the question is whether we can deal with determinant, which is a better object than the permanent. And yes, if we add some signs. And the signs should be Kasteleyn signs. And the condition is the following. The alternating product of Kasteleyn signs along each simple phase of degree to k is -1 to the k plus 1. One can always choose Kasteleyn signs to be real ones, so just plus and minus, plus -1. However, it's convenient to deal with complex signs, and this is what we will do. And for any choice of Kasteleyn signs, which satisfy this Kasteleyn condition, the partition function is given by the absolute value of the determinant. And the important corollary of this theorem is that all local statistics for the Dimer measure can be computed using the inverse Kasteleyn matrix. Okay, and for the uniform Dimer model on the square lattice, so where all weights on all edges are just ones, Kenyon proposed the following Kasteleyn weights as shown on the picture. So around each white vertex, put weights 1, I, -1, and -I. And first of all, it's easy to check that weights defined in such a way are Kasteleyn weights, so they satisfy Kasteleyn condition. And the main advantage of choosing weights in such a way is that with this choice, the inverse Caseline matrix considered as a one-point function is discrete holomorphic. So indeed, note that the inverse Caseline matrix times the Caseline matrix itself is the identity matrix. Now, if we think about one row of the inverse Caseline matrix, it corresponds to some fixed point v prime, fixed wide point v prime. And we can think about one row of the inverse Caseline matrix as a function defined on black vertices. Then note that at each column of the Caseline matrix, there are just 4 non-zero elements, which are 1, i minus 1, minus 1, corresponding to those edges. Therefore, it gives a relation for values of the inverse Caseline matrix, which is the following one. And it is 0 for all around each white vertex except the v prime, which is fixed. For v prime, this is 1. And this relation is nothing else as a discrete version of Cauchy-Riemann operator. And the main tool for establishing, one of the main tools for establishing the convergence of two-dimensional lattice models to the conformally invariant scaling limit is discrete version of complex analysis and potential theory. Now, let me comment a bit more on this slide. And I'm going to switch to my small blackboard. So let us discuss the general strategy, how to use discrete complex analysis to show the convergence of 2D lattice models on the example of uniform domino tilings on the square lattice. And here is the general strategy. So the idea is the following. Given some 2D lattice models, in our case, domino tilings, we're looking for some discrete holomorphic observable which satisfies some local relations. And later we want to think about these local relations as discrete holomorphicity. Then we take the object in which we're interested in. In our case, this is the height function, the gradient of the height function, or the fluctuations of the height function. And we want this object to be written in terms of these discrete holomorphic observables, which are also uniquely defined by some boundary value problem. And then what we do, we reduce all probabilistic equations actually to convergence of some, to convergence in boundary value problems of some functions, of discrete holomorphic functions to its continuous counterparts. This is a general strategy, and let me show it how it works on the example of the uniform domino tilings on the square lattice for some special type of approximations. Okay, so now we deal with uniform domino tilings. So all edge weights are just ones. The Kasteleyn signs are chosen as we already saw, 1i minus 1 minus i. So this is the theorem that the partition function can be evaluated at the absolute value of these Kasteleyn matrix. And now let us think about the inverse Kasteleyn matrix. Note that if I consider two neighboring vertices or squares B and W, then the absolute value of the inverse Caseline matrix at this domino is nothing else as the absolute value of the ratio of the determinant given by the matrix K without corresponding rows and columns to vertices W and B divided by the whole determinant of the matrix, right? This is just a definition of the, I mean, this is how to compute the elements of the inverse Caseline matrix. And note that in the case when B and W are just neighboring points, what is written here by this theorem, this is the number of domino tilings of the domain without this rectangle, right? Or in other words, this is the number of tilings of the whole domain which contain this domino, BW. So what is written here is just the probability to see domino BW in the random configuration of this domain. Dimer configuration of this domain, right? So the inverse, the absolute value of the inverse Caseline matrix is the probability to see the corresponding domino in the configuration. Now note that how it's related to the height function, right? Just, oh, you don't see this? Now you do. The gradient of the expectation of the gradient can be written in terms of probabilities, clearly. And the probability is given by the inverse Caseline matrix. Therefore, in a similar way, all moments of the height function can be written in terms of inverse Caseline matrix. And now, if I'm interested in proving some convergence of the fluctuations of the height function, it's enough to check that, okay, if we want to prove the convergence to GFF, it's enough to check that all moments of the fluctuations are the same as the moments for the GFF. And now all moments can be written in terms of inverse Caseline matrix. So I reduced the question about height function to the question about inverse Caseline matrix, right? The next step is to reduce the question about inverse Caseline matrix to convergence of some discrete holomorphic functions. So let's do this. Note that given the definition of weights, how we chose them, or actually how Rick proposed to choose them. Note that the inverse Caseline matrix, considered as a function on black vertices for one fixed white, is real on one type of black squares and pure imaginary on the other type of black squares. So for a fixed W, just because of how we define them, let us split black squares into two types, just line by line. This is type 0, type 1, type 1, type 0, and so on. I hope it's clear from the picture how we split black squares into two types. And then on one type, the values of the inverse Caseline matrix with a fixed white argument are real, and on the another type, it's pure imaginary. Okay, so now let me define the function on black vertices with a fixed one, with a fixed white. So let me just think about this object as a one-point function, which lives on black squares. Then, as we just saw on this slide, this identity, that the product of the Caseline matrix and the inverse Caseline matrix, implies that this function satisfies this identity for each W which is not W0. And this is the discrete version of a Cauchy-Riemann equation. So what we get the discrete function which satisfies some local relations. And we want to think about these local relations as the discrete holomorphicity. So we get a discrete holomorphic function. And now what about boundary conditions? Let's see what's going on the boundary. Note that on the boundary, so this is a part of the boundary, we have a relation which is actually taking into account only 3 neighbors of this point, right? Because we don't have this vertex in the graph. So, and then K times K inverse is identical matrix implies that we have this relation. What I can do, I can extend this function on black faces to be 0 on this boundary square. So just define it to be 0, which means that, okay, now we have a discrete holomorphic function. So it satisfies those relations. It is a discrete holomorphic function with the 0 boundary conditions on the boundary. And the discrete holomorphic function is defined uniquely by those boundary conditions. So what we did, we just reduced the question about the convergence of, let's say, of the inverse Caseline matrix to the convergence of some discrete holomorphic functions that satisfy some boundary conditions. Note that we even can say more in this case. There is a very good notion of discrete harmonic functions. So if we take our discrete holomorphic function and consider the equations, the discrete version of Cauchy-Riemann equations on 4 white squares, which are neighboring of some black one, then it's easy to check that if you just add all of them, then we get that the discrete Laplace at this black square is 0. So in other words, both real part and imaginary part of discrete holomorphic function are discrete harmonic, which is actually a good sign because we know that for continuous holomorphic function, its real and imaginary part are both harmonic one. And for discrete harmonic functions on the square lattice, with the choice of discrete Laplacian as we discussed, one can easily prove that, let's say, the green function converge to the continuous counterpart. So the discrete green function indeed converge to the continuous green function. So Rick used this approach to show that in the case of temporal approximations, so what are the temporal approximations? We already introduced 2 types of black squares. And let us consider a discrete domain on the square lattice where all corners of those domains are of the same type of black squares. Recall that on one type of black squares, the real part of our holomorphic function lives, and on the other type, the imaginary part of our discrete holomorphic function lives. So then these type of approximations give us discrete holomorphic functions where the real part on the boundary is 0. So what we know about the real part of the this discrete holomorphic function, first of all, on type of B0, those are real functions. It is discrete harmonic everywhere except the neighbors of our fixed white square, where it have, okay, at one of them, the Laplacian is 1, and another one, the Laplace is -1. And it is 0 everywhere on the boundary. Note that this is a discrete version of the derivative of the green function. And indeed, Rick showed that in the case of temporal approximations, so we have some domain which is approximated by temporally types of discrete domains, then the real part of the inverse Caseline matrix converges to the derivative of the green function, right? And this allows us to, if we already know the scaling limit of the inverse Caseline matrix, then as I mentioned before, we know the limit of moments of the height function, because all of them can be written in terms of the inverse Caseline matrix. And how to, just a comment, how to prove the convergence of the inverse Caseline matrix or of this discrete holomorphic function to its continuous counterpart. Okay, there are 3 steps. First, you should show the precompactness of the family of those discrete holomorphic functions. Then we know that in this case, we have a very nice boundary conditions. And we show that in the limit, they stay the same. We still have some boundary conditions. And the next step is to show the holomorphicity. And here, the Marianna theorem helps. You just check that the integral along each closed contour is 0. So, and then by boundary conditions plus holomorphicity, such a function defined uniquely, and we get the scaling limit of the inverse Caseline matrix. So what's the problem for, let's say, general type of approximations? Note that not any discrete domain which you can draw on the square lattice have such a nice boundary conditions. And here is the problem. In general, this is not true that you can identify discrete boundary conditions in some nice way to get the convergence or to get the notion of the continuous boundary value problem. What it is? Oh yeah, right. Here is another reason why some very nice discrete harmonic functions appears in the case of temporal domains. It is known that there is a bijection between configurations between dimer configurations on temporal domains and uniform spanning trees on corresponding graphs. So here is a picture. Let us consider a graph on the one type of black squares, and here is one spanning tree on such a graph. Then I hope it's clear from the picture how to construct from a spanning tree the corresponding dimer configuration. You just start from the leaf, you consider the path from the leaf to a root, and you start drawing the corresponding dominoes along this path. Then you get some dominoes on part of the domain, and the rest of the domain can be tiled by dominoes only in one way. So this is defined uniquely. So anyway, there is a bijection between dimers on temporal domains and uniform spanning trees on corresponding graphs. And yep, okay. Let me switch back to my slides.
So I have a question.
Sure.
Of course, in discrete setting, not all domains are temporally domains. But if you want to show some convergence, what can you approximate any region with a temporally domain?
Yes, you can approximate any region with a temporally domain. However, let's say if you think about, okay, like this is true that you can approximate any region by temporal domain. What is not true if you think about any flat boundary conditions, then any domain is a temporal one. for example, think about this picture. Probably you don't see it. Let me try to zoom it. So this is an example of flat boundary conditions for the height function, right? We see that the random dimer configuration is there is nothing frozen near the boundary. However, now if you think about, okay, I switched too early to the, just a second. Let us think about domain with a boundary like this. Then our harmonic function lives on those squares, and it is real on those ones and pure imaginary on these ones. And the boundary conditions which you get in this case is like, okay, you have here the imaginary part of this function is 0, here the real part of this function is 0. And it's absolutely not clear what does it mean in the limit. And why we are interested in different types of approximations. Let's say if you think about the convergence of the interface in the double dimer model, and you want to use the usual approach where to show that the interface satisfies, that it is conformal invariant, that it satisfies Markov property, then when you start drawing a path from the boundary, then in new domain, which is obtained from the given one minus our path, is not a temporal domain anymore, right? Because this is some random path going from the boundary. So this is another reason why we are interested about in different types of approximations. However, it's just interesting question in itself. But if you want an application, why we are not happy to deal only with temporal approximations. So this is one of the reasons. And here is an example that, okay, like boundary conditions are not so nice as we want them to be. The dimer model is super sensitive to the microscopic behavior of the boundary. In general, even in a flat case, this is not true that you can always identify some nice boundary conditions. Even more, this is not true that if you think about the scaling limit of the inverse Caseline matrix, then you can show that there is a subsequential scaling limit. However, it is not unique. Even in some simple cases, for example, if you just think about domains composed by squares 2 by 2, like general type of approximations, this is just not true that there is a unique scaling limit. There is a sequential, I mean, it's easy to see, to show precompactness, like there will be a subsequential scaling limit. However, it is not unique, so it's not a well-defined scaling limit. So let me go back. Did I answer to your question? Okay. Okay, so now the main idea here was that, okay, like if we define the Kasteleyn weights in such a way, then we can think about Caseline matrix as a discrete version of a d-bar operator. Because then the inverse Caseline matrix, of course, can be seen as the discrete holomorphic functions, since this is clearly the function in the kernel of the Caseline matrix. Now, what about general weighted planar bipartite graph? Can we always think about the Caseline matrix as a discrete Cauchy-Riemann operator? Okay, on one hand, we can always define on a discrete level the function to be discrete holomorphic if it is in the kernel of the Caseline matrix. The question is how this discrete holomorphic function correspond to the continuous counterparts. So we also want our embeddings to have a nice version of the discrete holomorphic functions on it. This is another property for our embeddings, which we want to hold. And we saw already that in the case of square lattice, there is a good notion of discrete d-bar operator. Note that there is no unique definition for the discrete version of discrete Cauchy-Riemann operator or Laplace operator. And the most known ones are on the square lattice, and we just discussed them. In this case, things work smoothly. What about general weighted planar bipartite graphs? Is there a way to embed them in such a way that the Kasteleyn weights given by geometric picture also describe a nice version of d-bar operator, discrete version of d-bar operator? Okay, and now how much time do I have? Like 10 minutes or so, right?
Yeah, take your time.
Okay. What I do next, let me finally define you the new class of embeddings. So what are they? Suppose that we start with a bipartite graph, which is embedded in a certain way that each face is a cyclic polygon. So each face inscribed in some circle. And assume also that each bounded face also contains a corresponding circle inside it, like it's shown on the picture. Then clearly we also have an embedding of the dual graph, right? If we just take centers of this circle pattern, it gives us an embedding of the dual graph. And what we're interested in, we are interested in circle pattern realizations with an embedded dual graph. Note with an embedded dual graph as the centers of this circle pattern. Note that the circle patterns themselves are not necessarily embedded. So what does it mean? Here is an example. Let us consider this small portion of planar bipartite graph together with its dual. And this is a circle pattern realization with an embedded dual. So what do I mean by realization? Note that each face of the planar bipartite graph, all vertices of this face are indeed lies on the same circle. However, we have some edges which correspond to our planar bipartite graph, which intersect on this circle pattern realization. So this is not an embedding, right? Proper embedding is if you can draw it in such a way that edges do not intersect. Here they do intersect. This is edges that correspond to these two. However, if we now take the centers of the circle pattern of this picture, then it gives an embedding of the dual graph. So for the dual graph, it is an embedding. But circle pattern realization for the planar bipartite graph itself, this is not an embedding. And we don't care about realization of bipartite graph itself. We only care about the embedding of the dual. And now, if we have an embedding of the dual, I can associate each face to the corresponding vertex. So for example, if we think about this black vertex, then it corresponds to this black point on the circle pattern realization and also to this black face for the embedding of the dual graph. And what I'm going to do, I'm going to associate actually vertices with those faces instead. I'm going to embed the dual graph and think about bipartite graph, initial bipartite graph itself as a, okay, colored faces of the embedded dual. Here is definition, a little bit different definition, which we use in the another project of the same embeddings. So a t-embedding is a proper embedding, meaning that all edges are straight segments and they do not overlap. Also, the dual graph is a bipartite one, meaning that we can color faces of such pictures in chessboard coloring in black and white, such that neighboring faces have different color. And the last important condition is that those embeddings satisfies angle condition around each vertex. So the sum of black angles around each inner vertex is the same as the sum of all white angles, and both of them are pi. Now, let me explain you, let me convince you that those two definitions define the same object. And I guess that's it, what I want to do for today, maybe, unless you have some questions. Okay, first of all, let us show that the centers of circle patterns satisfy angle conditions, right? This is the only thing which I need to check, that each circle pattern corresponds, each centers of circle patterns correspond to the t-embedding. Okay, note that the intersecting point of two circles are symmetric with respect to the center line, right? Therefore, those two angles are the same. And now if we consider next these two circles and so on, we clearly obtain that the sum of all black angles around one vertex is the same as the sum of all white angles. Therefore, each circle pattern, centers of circle pattern, satisfies angle condition. Now, starting from the t-embeddings, let us construct a circle pattern realization. Okay, choose any point on the plane that corresponds to this white face and reflect it with respect to the dual edge to get the position of the corresponding black face. Now, since t-embedding satisfies angle condition, this procedure is consistent, right? If I go around one vertex, then I finish with the same vertex. Then I can start doing it around next vertex of the t-embeddings and construct the whole t-embedding. Oh, sorry, the whole circle pattern realization. So, okay, this is the same definition of the same object. This is two definitions of the same object. And given, if we have the t-embedding, how to define a dimer model on it? So we start with a nice picture. We have these colored in black and white faces. We definitely have a bipartite graph on it. How to define the weights for the dimer model on this bipartite graph? So the weights are given by the corresponding vectors. So for each two neighboring faces W and B, we define the weight, Kasteleyn weight WB on this H as the corresponding vector, and let us decide that we always orient it in such a way that the white face is on the left. Then recall that we want these weights to be Kasteleyn weights. What does it mean? We want to check that they satisfy Kasteleyn sign condition, where the Kasteleyn sign condition is the following, that the alternating product of weights along each face is positive or negative depending on the degree of the corresponding face. Okay, note that the faces of bipartite graph correspond to the vertices of our t-embedding. And now what is the ratio of two neighboring Kasteleyn weights? Note that the argument of this ratio is nothing else as the argument of this angle, right? We have two complex numbers, one corresponds to this arrow, another corresponds to that one. And if we divide one by another, we obtain the argument of the ratio, which is just the angle of this white angle. And then this condition, the fact that the alternating product is positive or negative depending on the degree of the simple face, is equivalent to say that the sum of white angles is pi modulo 2 pi. But okay, in our case, it's just pi because we have an embedding and this is addition. Therefore, weights defined in such a way on our bipartite graph, they are Kasteleyn weights. So what we did, let me just a small bottom line. We introduced t-embeddings of the dual graph, and we define Kasteleyn weights on it. But this is not what we wanted. Recall that the goal was a given bipartite weighted graph to construct the embedding such that these geometric weights given by the embedding, they define the same probability measure. And this is the question to discuss next time. So yeah, let me maybe stop for today just with this definition.
Well, thank you very much. If there are questions. So I have not understood very well. What is the so you constructed the final timer model with the Kasteleyn weights. But what is the relay? Is it one-to-one, like tau embedding and the Kasteleyn timers? I don't understand very well.
So like the goal is to show that given any planar bipartite graph with real Kasteleyn weights, we can embed it in such a way that I just explain you in which way, right? And I explain you how to define geometric Kasteleyn weights on such embedding. The question is whether these weights and initial weights define the same probability measure, because we want to deal with given weights. We want to deal with a given probability measure on graphs, and we want to draw them in such a way. So, and I claim that one can always embed a graph in such a way, and such embedding is actually not unique unless you fix the boundary conditions. So yeah, like here, these embeddings they are not unique unless you ask some boundary, unless you fix some boundary conditions. And there is a way to fix these boundary conditions in such a way that indeed in the limit it gives a correct conformal structure for the fluctuations. Like if you just think about discrete setup, then and you just want to embed it, then such embedding is not unique. However, later on, we want to prove convergence of such embeddings. And then there is a question, okay, you have many embeddings. Is there one of them which is better than others? Yes, there is. But yeah, this is the next step.
So the idea is that this t-embedding is the best embedding to prove convergence.
Yes, first of all, the important part of this is that on those t-embeddings, we can introduce discrete holomorphic analysis. And this is our tool. I tried to explain you using the example of Kenyon results. What is the general strategy? So yeah, these embeddings are nice embeddings where we can prove the convergence. They describe conformal structure, and the main tool is discrete holomorphic analysis.
So what do you mean by one embedding is better than the other?
For example, in the case of biperiodic bipartite graphs,
Yeah.
okay, we can, for any biperiodic bipartite graph with biperiodic weights, we can embed the dual graph as a t-embedding. And such embedding is not unique. There is a one parameter family of such embeddings. However, for like, I didn't explain you what is the origami map.
Yeah.
But I mentioned that I wanted to be small in the limit. So in the biperiodic case, if I also ask this origami map to be bounded, which means that in the limit it's indeed converged to 0, then such embedding is unique. And this is the setup in which we can prove the convergence. In this sense, one embedding is better than others. However, all of them are t-embeddings. So there is some additional condition.
Mm-hmm. I see.
So I was curious, so like because you can view the inverse Kasteleyn matrix as basically a determinantal point process kernel, you can think of this as having a determinantal point process where the kernel is characterized by, some sort of discrete differential equation. In this case, the fact that this gives you a discrete holomorphic function. Do you know of other examples of a determinantal point process where the kernel is characterized by some differential equation or discrete differential equation?
No, I don't. The short answer is no, I don't. But like in this case, that this is determinantal point process. This is, this is a consequence of the Daimer model. Let's say, for example, we were like in general, as I mentioned, we just were looking for some observable which satisfies some local relations. And just in this case, this observable is the inverse Caseline matrix, and then, okay, function B in the kernel, we want it to be a discrete holomorphic. However, let's say in the Ising model, the picture is a little bit different. There is no determinantal point process, but still there is a discrete homorphicity. So I don't know other examples where it is the same.
I see. Okay, so it sounds like maybe this isn't the right analogy to draw.
Yeah, I know, I'm not sure, yeah.
Okay, thanks.
So along those lines, hear me by the way? Just making sure. Yeah, so along those lines, you had a specific choice of Kasteleyn weights in order to do this, to have the discrete holomorphicity. What happens if you, like suppose you choose some other, you apply this sort of gauge transformation. Does that translate to anything nice on the level of these functions, or does that just sort of ruin whatever structure?
Okay, choosing the the gauge transformation doesn't change the probability measure.
Right.
So all those Kasteleyn matrices, which you can obtain by gauge transformations, they are, in the probabilistic sense, they are the same.
Mm-hmm.
So there is a class of weights which define the same probability measure. And what we're looking for a gauge where we can deal with the complex, discrete complex analysis. This is actually the point, the main point.
Yeah. So if you do change, so let's say you found a nice, discrete holomorphic structure, and then you apply the sort of gauge transformation at a vertex, right? Like you sort of just update the weights around. Does that sort of, deform this thing into something that's reasonably interpretable, or does it just sort of completely,
It completely breaks everything.
Okay. Yeah.
Even if you just think in this simple setup for the square lattice, right? One can choose signs. I mean, like, this is very important choice of these signs, which is the same as to choose the gauge of Caseline matrix, because this is exactly what is equivalent to discrete Cauchy-Riemann operator. However, you can choose all signs to be just plus or minus ones. And then it completely doesn't work. You don't have any discrete homomorphicity. There is no nice interpretation. So yeah, the choice of the gauge is very important. And if you change it, okay, maybe it's not unique. There are nice modifications from one to another. However, if you just break it randomly, I mean, like arbitrary, then it doesn't work anymore.
But wait, if you do a gauge transformation, wouldn't this then give you a function which is not annihilated by the discrete d-bar operator, but like annihilated by the discrete d-bar operator conjugated by some discrete homomorphic function, or like something along these lines, which I guess is just not a nice object anymore, maybe?
Right, this is not a nice object anymore, and this is the reason, because those discrete homomorphic functions have nothing to do with continuous counterparts. So there should be a reasonable choice of discrete d-bar operator. It should approximate in a good way the continuous d-bar operator.
Right.
Okay, but the gauge transformation amounts to doing some sort of conjugation to the d-bar operator, is that?
Yes, if it is reasonable to the d-bar operator, then yeah, it works. But the question is, what are they?
Right. Yeah, the reason I ask is, I'm just sort of wondering if you were to have chosen a different gauge transformation and studied, whatever limit pops up on the other side, what is, this thing won't be holomorphic, but it'll be, like, what's the sort of transformation that you need to?
Like maybe you get something annihilated by the continuous d-bar operator conjugated by a continuous.
Something like that, yeah.
Harmonic
That's the sort of answer I was looking for, so.
Yeah, it's not clear, especially that you should like make sense of it in the limit. What is this gauge transformation? I mean, it should work well in the limit as well.
Right.
Yeah. I don't know. It seems to be a complicated question. At least, I mean, I don't know the answer.
Thanks.
So probably this is a stupid question. So you're kind of forcing the model to have these edge weights, so that this function comes out with some discrete holomorphicity, and then you show that, and then I guess that what you want to do is to show that the fluctuations of the height function go to the Gaussian free field. But what if the function does not have discrete holomorphicity? Then
so,
the
yet again, we don't force. Okay, we have some assumptions which are actually related to the weights, but this is not what you are asking, as I understand right now. We start with any bipartite graph with any weights. And then we are looking for a good good candidate in the class of gauge equivalent weights. Right? Given weights, I have a huge family of gauge equivalent weights, and I just want to pick one of them. And I claim that under some assumptions, there is a good one which describe a good d-bar, discrete d-bar operator. That's the point. So we don't want, like in general, we don't want to force weights to be some specific ones. However, of course, actually we do, because like, I mean, there are very bad choices when you will not have any convergence to the GFF, but we have some assumptions, but those are reasonable assumptions for a model, for the Daimer model. So like it is a more general setup than.
So are you saying that those assumptions guarantee that you can find a representative in your gauge equivalence class that has the discrete holomorphic structure?
Yep.
Okay.
Absolutely, that's the point.
Okay, so you're not forcing discrete homomorphism. Discrete homomorphism is a consequence of this very weak hypothesis.
You know, like I mean, we want some embedding such that, okay, like such that the fluctuations converge to GFF. Now the question is like, okay, what are other properties we want these embeddings to satisfy? And this embedding, to find this embedding, is the same to choose the one Kasteleyn weights of one Caseline matrix from the class of gauge equivalent ones. And we also claim that yes, this good one also satisfy nice discrete homomorphicity. There is a nice discrete homomorphicity on it. Like we can reformulate this question about the convergence in terms of like, okay, let us maybe think not about this super ambitious goal. Let us think about our goals. Whether there is a nice choice of Caseline matrix such that you can define a nice discrete holomorphic functions on it. And yes, this is also the answer. Those are t-embeddings or circle pattern embeddings.